All right. Last time I told you I thought that the presentation was between environmental and hydraulics. I was wrong. I double-checked the schedule, and that faculty candidate is coming at 2. And it's not 22:01. That's my office. I really need to stop making these announcement slides when I'm sleepy. It's next door in 11:03. Man, oh man, I'm all over the place today. I apologize. But he's given his presentation on sustainable and integrated water resources management. His background's environmental engineering, and if you're able to attend, you can get 10 bonus homework points for just writing a brief summary of what he talked about and what is your opinion about him being a professor at Marshall. And if you're in both this and environmental, you can get 10 points in each class for uploading the same response, if you're in both. So I just wanted to make that correction that it's at 2, and it's not in 22:01, it's next door in 11:03. So any questions about that? Okay, the other thing is that homework 1 is due on Wednesday of next week. We don't have class on Monday. Did you already know that it's a university holiday on Monday, so we've got the day off. So Wednesday is when the homework's due. We're going to talk a little bit more about the homework and work through an example related to that today. We're continuing in Chapter 7 of the book. So what we're talking about today is covered in sections 3 through 5 of Chapter 7. And I hope that you're taking the time to go through and read the book, because it's not enough just to listen to me. You need to also be reflecting and hearing it from another point of view and going through the additional examples that are in the text. That additional exposure will help seal the deal on your success this semester. All right. So last time we didn't get to shear velocity. So let me tell you what that is. It's just kind of playing games with the units and rearranging an equation to express shear stress in a different way. So if we just take the combination of this definition of head loss due to pipe friction in terms of shear stress, and we worked with this first formula a little bit in our first 2 class meetings, just the idea that when water is flowing through a conduit, whether it's a pipe that's enclosed or a channel that's open, either way, the stationary material that isn't moving, meaning like the concrete of the channel or the pipe material, it's stationary and it's resisting flow. And it resists it by applying a shear stress to the fluid. So that's what this is. Now, also, we have an empirical equation in the Darcy-Weisbach that describes the quantity of energy loss due to pipe friction in terms of the length, velocity, diameter, and this friction factor F, which we can get from the Moody diagram, if you'll remember. So if we set those two equal to each other and rearrange things, what we get is that the shear stress divided by the density is equal to the friction factor times the velocity squared. So there's this relationship that we end up with velocity on the right-hand side of the equation, and if we further rearrange things and look at the units, what that's telling us in terms of the units, if shear stress is newtons per meter squared, and if density is kilograms per cubic meter, but it being in the denominator, what we do is we'd say multiplied by meters cubed divided by kilograms, and then we break down what is a newton. A newton is a kilogram meter per second squared. And so we just keep breaking things down to their base units and then cancel out. What we end up is that this expression on the left, shear stress divided by density, is having units of meters squared per second squared. So the idea with shear velocity is just to say, hey, meters squared per second squared, that sounds a lot like meters per second. So if we took the square root of shear stress divided by density, we could have this quantity as units of meters. So that's what they do with shear stress, is they say, let's take the square root of the shear stress divided by density, and then we have some expression of the magnitude of the shear stress, and it's got these novel units of meters per second, length per time. So what it boils down to is that we could relate shear stress, velocity, and friction factor in this way. And so this is just talking about the amount of shear stress at the wall of a pipe as a function of the velocity of the flow of the water, and then the roughness of the pipe expressed as the friction factor. So I think you've got a homework question that asks you to relate shear stress and friction factor, and this is the approach that you can use for that problem. Any questions about shear velocity before we move on? All right, we have an open channel here, a rectangular open channel. No, trapezoidal. I really am discombobulated today. This is a trapezoidal channel, and you're going to get really good at dealing with the geometry of a trapezoidal channel, because most engineered channels that are carrying water, they use the trapezoidal shape, especially if you've got like soil or grass lining on the edges. You can't have a vertical side slope because just the soil will collapse. If you have concrete, maybe you could do that. You know, concrete can hold an angle like that. Rock, if you're chiseling a channel through rock can handle a vertical side slope. But that's expensive to chisel through rock. That's expensive to line a canal with concrete. What's cheap is grass lining, or just leaving it with clay, or putting in maybe like a plastic liner of some sort. And so to do that and ensure slope stability, we'll have these gently inclined side slopes, which means when we're calculating things like area and wetted perimeter and hydraulic radius, now the geometry gets a little bit more tricky than it would here. Area here is really easy. We've got some depth, we've got some width. So the depth of flow is just, the cross-sectional area is the depth times the channel width. But in a trapezoidal channel, it's a little bit more tricky. So the shear stress equation does apply in an open channel as well as inside of an enclosed pipe. And I wanted just to give you a first taste of the area, wetted perimeter type calculations for an open channel like this one. So you'll notice here that the side slopes are defined as some unit of vertical to some unit horizontal. And our book has a series of equations you could use to calculate area, wetted perimeter, hydraulic radius, and they define the side slope in terms of this variable t. And if you see t, for example, if it says t equals 2, what that means is that there's 2 units of horizontal distance for every 1 unit of vertical distance in defining the side slope. So t is just the horizontal component of the side slope, where the vertical component is set to 1. Does that make sense so far? Okay, good. So when we have steady and uniform flow, steady meaning that the flow conditions aren't changing over time. Uniform means that there's no disturbance like a log at the bottom of the river. There's nothing that's causing the velocity or depth to change in the direction of flow. That's uniform. We've got steady and uniform flow, then the three slopes that are important to us are all parallel to each other. So the first slope is the slope of the bottom of the channel. So if you see S naught, that's the channel bottom slope. So that's the slope of, it might be inclined, but the bottom of the channel is S naught. So now the water surface, see here where it says WS? That means water surface, and we can tell, even without that label, that that's the water surface because of the triangle, the little ripples, they're giving us that visual clue. So S sub W is the slope of the water. And then finally, this dashed line above the water surface is the energy grade line. Some texts refer to it as the total energy line, TEL. That dashed line, it's just the water surface plus the velocity head takes us up to the energy grade line. And you may remember that we've already seen the variable S sub F. That's the slope of the energy grade line, or the slope of the total energy line. So when you've got steady, uniform flow, these 3 slopes are equal to each other, meaning that the channel bottom, the water surface, and the energy grade line are parallel if steady, uniform flow conditions exist. Okay, so now about the geometry of a trapezoidal channel. Let's just say, what is the hydraulic radius of a trapezoidal channel in terms of B, Y, and T? So this lowercase b is the bottom width of the channel, and that's a pretty common variable, by the way. Y is pretty commonly used for the depth. The top width of a trapezoidal channel, some books label it as capital B, some books label it as uppercase T. Just try to keep that in mind. Most of the time I'm going to use a capital B for that. So how do we find out the hydraulic radius if we need to know the area and wetted perimeter? So let me just, for purposes of saving a bit of time, show you the solution to that one rather than asking you to derive it. I'd like us to make progress on other things, but let's say that we've got a T for the horizontal component of the side slope and 1 as the vertical component of the side slope. So how would we understand the area? So what I'm saying is treat that trapezoid as a rectangle in the middle and 2 triangles, 1 on each side. So here's a trapezoid, I'm writing it on the board, here's our water surface, okay. And imagine that those two have the same slope. Boy, that's a terrible drawing. Let's see if I can do a little better. All right. So imagine, what if we've got this part of it, which is b times y. I think everybody can see that the area of that center part, it's a rectangle, so it's the bottom width times the depth to get that component of the area. And then here is a triangle which has a certain height, and the height of that triangle is t times y. T times y is the height, and then y, I'm sorry. So y is that side of it, t times y is the combined effect of both of those triangles together. So think about, if you put the 2 triangles on the side together as a single rectangle, what's going to be the area of that? It's going to be the depth multiplied by the top component, and we're just basically slipping this one over and joining it with the other, so it's another rectangle. So the cross-sectional area, this is the center component, y times b, then y times ty is the area of these 2 side triangles. Okay, so now for wetted perimeter of a trapezoidal channel, that's talking about what is this part plus that part and that part. That's the wetted perimeter. Sometimes you just have the P instead of P sub W. Wetted perimeter. So that is, you can see obviously the bottom width B is one part of it, and then the side slopes, there's 2 of them. There's one on the right, one on the left, and each one of them is the square root of y squared plus ty squared. So ty is the distance across the top, so it's just saying we want to know the length of one of these. It's going to be y squared plus ty squared, and take the square root of that, and then we've got 2 of them. So 2 times that quantity. So that's the wetted perimeter. So hydraulic radius then would be the area divided by the wetted perimeter. Then I've got this note here, see page 301. There's a table on page 301 that has these calculations and others related to the geometric properties of a trapezoidal channel. So I think maybe in the homework assignment you need to do some just initial struggling with trapezoidal channel geometry, and I hope that these formulas will help you with that, for finding the area, the wetted perimeter, and then from that, the hydraulic radius. And then, if you know the hydraulic radius, you can relate the slope of the energy grade line, the shear stress, and the unit weight of water to find the shear stress is equal to the unit weight of water, hydraulic radius, and slope of the energy grade line. So any questions about the trapezoidal geometry or open channels in general? Okay, empirical resistance formulas. We want to have a way that we can predict how much energy is going to be lost when water is flowing through pipes or through channels. We don't want to always have to measure it. You can't just build a pipeline without knowing how it's going to perform in terms of the lost pressure as water's flowing through there. So one of the earliest formulas for trying to estimate the effect of shear stress and energy losses due to friction was the Chezy equation. And this isn't a history class, but it is still informative for us to know a bit about the Chezy equation because its progeny, the equation that came after, is very closely related to the Chezy equation. There's an improved version that we're going to continue to use today called the Manning equation. So in the Chezy equation, the big observation, the aha moment, was that what you could do was come up with a friction factor. Here it's designated as a C value, which corresponded to the roughness of the pipe, where a low value of C was very rough, a high value of C was thought of as very smooth. And if you multiplied by that by the square root of the hydraulic radius times the slope of the energy grade line, then you could estimate the velocity of flow. So that was just one of the first attempts, which came from just observing a lot of different scenarios. It's kind of a curve fitting approach. By curve fitting, what I mean is you got a bunch of experimental data out in the real world, and then you came up with this fudge factor, C, that kind of makes the right-hand side of the equation describe your intended target, which is describing what's the velocity. So it's not going to be perfectly accurate, but it's better than knowing nothing about what might happen. This empirical equation is not dimensionally homogeneous. So if you look at the units on the left-hand side being meters per second for velocity, you're not necessarily going to get those same units in an empirical equation by what's on the right-hand side of the equation. But that's okay. It can still be useful even if it's not 100% accurate, and if it's not based exclusively on the underlying fundamentals of physics. These observed equations that are empirical in nature can still be useful to us. So Chezy equation it evolved and was replaced by Manning's equation, which we'll talk about in detail, mostly in the second half of the class. But on page 201 of the book, there's just the observation that you can relate the Chezy friction factor C with the Darcy-Weisbach friction factor F using this formula. So there is some way to tie the two friction factors together. One of the things that makes the Chezy equation a little bit, I wouldn't say annoying, but it's not as good because the friction factors are unit dependent. So you have a different friction factor for SI units versus traditional units, and that's not always true for the other empirical equations that we've got. So that's the Chezy equation. Now let's talk about velocity distributions briefly, and think about a circular pipe that water's flowing through in this circular pipe, and it makes sense that the further away you are from the edges of the pipe, the faster the velocity of the flow is. And so if you've got laminar conditions, which are associated with relatively low flow rates, it's typical to observe a parabolic velocity distribution, where at the center of the pipe, there's a much higher velocity than at the edges of the pipe where the resistance is applied. But when you increase the flow velocity into the range that's associated with fully turbulent flow, you won't necessarily see that same parabolic distribution because of randomness inside of the pipe. A fluid particle in laminar conditions that's flowing through the pipe, if it starts in the center of the pipe, it's more or less going to stay in the center of the pipe the whole time it's flowing through under laminar conditions. If flow conditions are turbulent, it's going all over the place in its gradual movement towards the right. There's a lot more randomness, and because of that, the velocity distribution is more flat around the center, and of course it still tapers to zero at the edges because of the no-slip condition. So I wanted to point out those two general types of velocity distributions because we're going to be talking about the range in which there's this layer near the edge of the pipe where the velocity is low. So velocity is high in the center of the pipe. I think everybody understands that and gets it at an instinctual level. And close to the pipe, the water is at the same velocity as the pipe itself, which is to say 0. So there's this certain layer where the velocity is either 0 or very slow, where even if in the center of the pipe conditions are turbulent, if you get close enough to the edge of the pipe, there's a layer of laminar flow in the vicinity of the pipe material. And that's going to be important to us when we talk about estimating energy losses, is the thickness of this boundary layer. So a boundary layer is just, you can think of it as a cushion, where the flow conditions are a little bit different than in the majority of the pipe's cross-section. Like if the water is flowing around at a uniform velocity distribution, so this is showing that, if we take a side view, and here's a piece of material. It could be a sheet of metal, for example, or it could be the boundary of a pipe. But if you just have a piece of stationary material, which is that thick black line, and it's encountering water that's flowing from the left towards the right with a uniform velocity distribution, as the fluid encounters that stationary surface, the fluid that's closest to the stationary surface has a reduced velocity. And the further away you get from the surface, the higher the velocity is. So that's called a no-slip condition. The idea that since fluid has viscosity, it's subject to the effects of friction, and its velocity is going to slow down under the influence and in the immediate proximity of that pipe. So fluid velocity decreases in the vicinity of the surface, and initially the velocity slowing down, but it will reach some equilibrium where it was going through a period of transition where the water had a uniform velocity distribution. It's kind of getting settled in, and eventually you'll get into equilibrium where the velocity is not changing anymore in the direction of flow, but there is a different velocity at the surface than as you get further away from the surface. So is everybody following the idea of a boundary layer so far? Any questions about that? How thick it's going to be depends on the type of fluid that's flowing. So if you have alcohol flowing through a pipe, alcohol has very low viscosity compared to, say, glycerin, which is very viscous. Glycerin is like honey on a cold day. If you tried to pour it out of a beaker, it would hardly move at all. Very viscous. And so the thickness of the boundary layer depends on lots of conditions, like the velocity of the flow, the fluid properties, and also it depends on the surface. So if you have polished plastic, which is very smooth, the thickness of the boundary layer is going to be different compared to if you have a very rough concrete, like the kind of finish maybe you've seen when people will brush with a broom over wet concrete. It puts a texture on it that's pretty rough. And so you have to be aware of the pipe materials to understand the thickness of the boundary layer. And if we increase the velocity, then the thickness of the boundary layer will decrease. And if the velocity encountering the pipe slows down, the thickness of the boundary layer gets larger. The boundary layer is that zone where the fluid conditions are laminar. All right. So this is one of those diagrams that I'll talk about for 10 minutes, but really you should look at it for 20 or 30 to really think about what is this talking about. This figure's a little counterintuitive. So it says here, here's the center of the pipe, and on the horizontal axis is increasing shear stress. And here's the edge of the pipe. So what we're talking about is at the edge of the pipe, the shear stress that the pipe is applying to the water is at the highest. And that makes sense, that the water is getting the most, like it's being pushed on, you could think of it as, by the pipe at a maximum amount right at the surface where the two come into contact. And then the further away you get from the edge of the pipe, so now as I go up in this diagram, I'm going towards the center of the pipe, then the amount of shear stress is decreasing. So that's kind of why there is, let's say, more flow at the center of the pipe than there is at the edge. The two things go hand in hand. If you've got less shear stress influence at the center of the pipe, then obviously the flow velocity is going to be greater. So this is showing the shear stress under laminar conditions, how far into the pipe, or how far into the liquid, how far into the liquid the shear stress influence is extended. So if you've got relatively low velocity, then the shear stress basically has exerted itself even before you get to the center of the pipe. So we want to know how thick is this layer. Here you can see we're defining a certain zone as the thickness of the boundary layer. We want to know, for that laminar sublayer, how thick is it? Because if it's really thick and it completely covers the roughness of the pipe, then one set of flow conditions exists. Or if the roughness of the pipe extends beyond the boundary layer, then we estimate the pipe friction in a different way. So we're often interested in estimating how thick is the boundary layer based on the flow conditions. Because if you've got a fast velocity and high shear stress, that's going to mean you've got a small boundary layer thickness, but a low velocity and low shear stress means that the laminar, this laminar zone, is larger. Pipes are characterized by how rough they are, and the equivalent sand roughness is given units of length. And the rationale for that is, actual materials like wrought iron or concrete, they have irregular surfaces, and it's effectively random, but we estimate how rough they are by expressing it in terms of what if there was some sand that was adhering to a pipe. What would be the diameter of the sand grain that gives you the equivalent amount of roughness as this random irregular surface? So that's why it's called equivalent sand roughness. So for example, glass is very smooth. And how smooth is glass? Glass is so smooth that if you're going to have a pipe that was as smooth as glass, but it was coated with sand, the sand grains would have to be this small. That's how small the sand grains would have to be to have the same effect on energy loss due to pipe friction as a glass pipe. So concrete is really rough. How rough is concrete? It's so rough that if you had to have an equivalent roughness with spherical sand grains, the diameter of those spherical sand grains would be 3 millimeters. So that's why we call it equivalent sand roughness, is it's just a way of relating something that we do know, like the properties of sand and the effect that that would have on water flowing through a pipe, with something irregular and difficult to characterize because of its randomness. You can see we've got both SI units and traditional units. You may want to put a special star in your notes to help you come back to this. It's also in the book, but you'll need this, I think, for some of the homework assignments. This equivalent sand roughness goes into one of the formulas that we use instead of using a Moody diagram. There's other ways to estimate F than using the Moody diagram. The Moody diagram, it's okay, but it's a little bit annoying because if we want to automate our calculations, we don't have to want to go to some paper diagram if we want the computer to be doing the calculations for us. And so there's other equations we can use to estimate F, and those equations use this as one of the input factors, is how rough is the material of the pipe. Any questions? Can you believe that they used to make pipe out of wood? Wood stave. I guess it's like barrels. We all know, like, they put whiskey in barrels and wine in barrels. Well, that same technology was used to carry water back in the day. And luckily we've moved on, because I think wood is irregular, it decays over time. So, but it is interesting that we are able to characterize the roughness of wood pipe. Okay, so how thick is the boundary layer? Well, it depends on the flow conditions, it depends on the viscosity of the fluid. So Morris and Wiggert together came up with an empirical equation for estimating the thickness of the boundary layer. And what they said is that if you know the kinematic viscosity of the fluid, and then they had this 11.6 fitting factor that they related along with the shear velocity, then that's how they thought you could estimate how thick is the boundary layer. It's with this empirical formula and estimating the shear velocity, which depends on the fluid density and the magnitude of the shear stress. So with that, if you calculate the thickness of the boundary layer and it's more than 1.7 times thicker than the equivalent sand roughness, then what that means is that the thickness of the laminar layer is greater than the roughness elements, and so it dominates. This is effectively hydraulically smooth. Hydraulically smooth is a classification when you can see here the ridges of the roughness are much smaller than the thickness of the boundary layer. So it's not going to interfere with the flow as much in the center of the pipe if your roughness elements are fully cushioned by this laminar zone, then it's hydraulically smooth. So if that's hydraulically smooth, you probably would guess that there's a hydraulically rough. Hydraulically rough is when these roughness elements extend into the bulk flow beyond the laminar zone by quite a lot. It's saying if the thickness of the boundary layer is less than 8% of the equivalent sand roughness, then that's hydraulically rough. So there's a big middle zone where it's neither hydraulically smooth nor hydraulically rough. And we'll get into the implications of that with our empirical equations for estimating the friction factor F. But this is just kind of laying the groundwork so conceptually you can think about that there is a zone in the pipe where conditions are laminar, even if in most of the pipe conditions are turbulent. Okay, so I want to give you some more practice on the ideas that go into that problem I showed you in class on Wednesday. Remember I gave you kind of a couple of hints for problem 8? Here's going to be some practice for problem 8 and applying the energy equation. So we've got an elevated tank and we're taking water to the building, and we know that we want, at the ground floor of the building, we want 350 kilopascals. So we know the length of the pipe, we know the diameter of the pipe, the flow rate, and then in this problem, it's just defining for us what is the friction loss. They're saying it's 16.4 meters is the given friction loss. So we're going to try and find out what's the water surface elevation, what would be the friction factor that applies in this case, what's the thickness of the boundary layer, and we're going to determine the pipe material with the given data that we've got. We're going to go back to that table and see if we can figure out, given all the performance that we're observing, what's that pipe made out of? Okay, but the first thing I want to do is help you a little bit in diagnosing how to use the energy equation. When you got a picture like this, like what does the system look like? So we've got a tank, which is basically going to a pipe that's then going to a building. Okay, so the most logical place to select as location 1 in the energy equation is your origin. In the energy equation, there's a directionality that's implied by the left-hand side having this 1, the right-hand side of the equation having the number 2, and then the head losses are on the right-hand side of the equation. What that tells us is that the amount of energy at 1 is greater than the amount of energy at 2, because as the water flows from 1 towards 2, some of the energy is lost due to pipe friction and local losses. So head losses, H sub L, includes those two classifications. Energy loss due to pipe friction, energy loss due to local losses. So 1 is at the surface of the tank, and 2 is at the base of the building. So this is location 2. And the water's flowing through the pipe at some velocity that we haven't calculated yet. So let's look at the energy equation. We got the pressure head at 1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to the pressure at 2 divided by gamma plus Z2 plus V2 squared divided by 2G plus the head losses. We don't know anything about the local losses, so let's just assume that the losses are entirely due to pipe friction here. So I'm just going to say H sub F, because H naught is 0. We're assuming that there's no local losses, which is fine. Okay, so here's location 1. It's got no pressure. Why is there no water pressure at 1? Because this is at the surface of the reservoir, which is open to the atmosphere. We're assuming it's got the water pressure at the surface is the same as the air pressure. We're working in terms of gauge pressure, meaning that the atmosphere of the Earth is our baseline of 0. So P1 is equal to 0. It's air pressure, which is 0. Okay, so we can cancel out the pressure head term. What's the velocity of the water in this elevated storage tank?
0.
It's effectively 0. Like maybe the water level's going down very slowly, but maybe there's water going into the tank. So even if the water level was going down a little bit, we could still neglect the velocity at location 1 because it's so small. So V1 is 0. Z1, that's what we're trying to find. What must be the water surface elevation in the water storage tank? So we're going to find that. Okay, what is P2, the required pressure at the building? This is the 350 kPa. kPa, what is that the same as? Anybody know what's a Pascal?
Newton per meter squared.
Good. Newton per meter squared is a Pascal. So when we say 350 kPa, we could also say 350 kilonewtons per meter squared. Why did I bother to make that substitution? It's because the unit weight of water is 9810 newtons per meter cubed. Each of the terms in this equation is going to have units of length. So we want to make sure that dimensionally, the things that we're substituting in make sense. So if I say 9810 newtons per meter cubed, I could also say 9.81 kilonewtons per meter cubed. So I've got kilonewtons per meter squared in the numerator, 9.81 kilonewtons per meter cubed in the denominator. That's, when I divide those out, that's going to give me units of length in that pressure head term. Okay, Z2, I guess by looking at the diagram, we can see that Z2 has an elevation of 20 meters. Okay, V1, that's not 0, because we're talking about the water as it's flowing through the pipe. So the water does have some velocity as it's flowing through the pipe at location 2. How are we going to get that velocity? Well, we know the flow rate, and we know the pipe diameter. Remember this little gem, V equals Q divided by area. And so our flow rate of 12,000 liters per minute, it would really be more useful if we knew that in terms of cubic meters per second. So I'm going to pause for a moment. I'm going to give you some time to crunch the numbers, substitute in what you know, and tell me, what is the elevation of the that tank? How high does it need to be in order to overcome the effects of head loss, overcome the elevation difference, and provide adequate pressure at location 2? Continue working if you're still plugging through the numbers. 12,000 liters per minute is 0.2 cubic meters per second. which gives us a flow velocity. If you calculate the area, area is pi d squared divided by 4. It's been decades since I thought about area in terms of radius. It doesn't even occur to me anymore that that would be a way of calculating the area. But pi d squared divided by 4 for a circular pipe gives us 0.04909 meters squared. So the velocity, the water's moving at a velocity through the pipe, 4.074 meters per second. That's pretty fast. In reality, it would be uncommon for water to flow through a pipe that fast. The reason why is you lose a lot of energy when water's moving that fast. Anyways, it's just an example. If we put all of this in to kind of find Z1, how high does Z1 have to be? It has to be 35.6 meters high in order to pressurize the pipe to the desired 350 kPa. Plus, it has to be another 20 meters high for the elevation of that building being 20 meters above the datum. Plus, you need to add 0.846 meters of energy for the velocity head, which is pretty small. That's why sometimes velocity head gets neglected, is because it contributes very little. Even when the water's moving like extraordinarily fast, like I told you, 4 meters per second is considered quite speedy, it's still just 0.8 meters of elevation head. And then the 16 meters of elevation head, which is associated with head loss. So you add them all together. I think it's interesting, and keep them separate for a while just to see like how tall does this tank need to be for different aspects. Because maybe your boss would say, wow, we don't want to make a tank that tall. Is there anything we can do? And you'd be able to say, oh sure, yeah, there's a couple things we could do. We could use a larger pipe that would reduce the energy loss due to pipe friction. Then we wouldn't have to have the tank as tall if we had a bigger pipe. Or you could say, well, we could lower the building, But besides that, it's physics and there's not a lot we can do if we want that 350 kPa at the building. So that's a required tank elevation. Any questions with this first part of the problem so far? What else did we want to know? What is the friction factor? Okay, so now we're back calculating F based on what we know about the given formula for friction factor, rearranging that for F, and then adding in the head loss, the diameter, G, pipe length, velocity. This is just for giggles. You won't usually calculate F like this. Normally, you'll estimate F with either like the Colebrook equation or the Jane equation or a Moody diagram. We're just doing this in reverse, I guess, to be cute. So that's the F value, 0.0194, and slope of the energy grade line. So this is important to reinforce the definition of what is the slope of the energy grade line. It's head loss divided by length. So the slope of the energy grade line, 0.0656. And then this last part about the boundary of the thickness of the boundary layer, according to the Morrison-Wigert criteria. So the thickness of the boundary layer, we're going to need to know what is the shear stress. So we use the slope of the energy grade line to help us estimate the shear stress magnitude. And this is water, so it's got a density of 1,000. And so now from that we can get the shear velocity. 0.2 meters per second is the shear velocity, which remember is just some expression of the magnitude of shear stress. And then we put that into Morrison-Wigert's empirical equation for estimating the thickness of the boundary layer, which has units of meters. So 5.8 times 10 to the minus fifth meters. So if we multiply that by 1,000, the thickness of the boundary layer is 0.058 millimeters. So it's a pretty small boundary layer. And then the last thing here that we wanted to know, determine the pipe material. We're out of time. We'll do that another time, or maybe not at all. So, just to revisit the announcements, remember we've got that presentation at 2. If you're able to join that, I'd be glad to have you there. We will not have class on Monday. So if you have questions on the homework, you can stop by my office, you can send me an email. And one last thing, call your parents. Tell them how your first week of classes went. My son's in college for the first time this semester. I'm just desperately interested to know how it's going, but I never hear from him. So this is your reminder to call your parents and let them know how much you like hydraulic engineering. See you next week.